All right, let's get into it. Today, we're not just going to crunch numbers. Nope, we're actually going to follow a story. And it's a story about a shape you see like everywhere. Think about the arc of a basketball shot, or even the shape of a bridge. We're talking about the story of the parabola. So, have you ever wondered what a massive home run has in common with your satellite TV signal? I mean, really. Well, the answer is this surprisingly simple, really elegant curve called a parabola. And the secret to its whole story? It's all hidden inside an equation called a quadratic function. You know, every great story needs a main character, a hero, right? Well, in the world of parabolas, our hero is this. Just this beautifully simple equation, y equals x squared. That's it. This is our starting point, the origin for every single parabola story we're going to tell. So, let's meet our main character. Here it is in its most basic form, this perfect U shape, sitting right there at the center of everything. We call this the parent parabola. Just think of it as the baseline, you know? It's the starting block for every adventure that follows. Okay, but our parabola, our little hero, doesn't just sit there at 0, 0. No way. Its story is all about transformation, about movement. Every single piece of its equation is like a command, telling it where to go, how to stretch, how to shift. And believe me, this is where the journey starts to get really, really interesting. All right, let's take a look at a specific journey. Check out this equation. Now I know it might look a little complicated at first, but trust me, we're going to start simple. Everything begins with our parent parabola. Good old y equals x squared, just chillin' at the origin. So what's the first move? It's that number 2 sitting out front. That's our first instruction. It tells the parabola to stretch. Stretch vertically by a factor of 2. It's like it's reaching for the sky, you know? It gets taller, narrower, a whole lot steeper. Definitely more dramatic. Okay, next up, we've got that x plus 1 inside the parentheses. Now this part can feel a little weird, a little backwards. You see a plus 1 and you think go right, but nope. It actually tells our parabola to take one step to the left. It's a key move, shifting it horizontally. And the grand finale, the final instruction, it's that -4 hanging out at the very end. This one's easy. It's a super straightforward command, just to move the whole thing down by 4 units. And just like that, our parabola has finished its journey. It's sailed right into its new home on the graph. And once you see it, you start seeing the pattern everywhere. Take this equation, for example. It's telling a very similar story, right? A vertical stretch by 3, a shift 2 units to the right this time, and then a jump 5 units up. Every number is a new command, a new chapter in the story. You know, every story has that big moment, the climax, the major turning point. Well, for a parabola, that climax is called the vertex. It's either the absolute bottom of a valley or it's the breathtaking peak of a mountain climb. It is, without a doubt, the most important point in its entire journey. So the big question is, how do we find this climax point? Well, the equation itself can give us the answer, and there are kind of 2 ways it can do it. If you have what's called vertex form, it's awesome. The climax is just staring right at you. You can literally just look at the equation and see the vertex is at -1, -4. But if it's in standard form, it's a bit more of a mystery. We have to pull out a special tool, this little formula, x equals -b over 2a, to figure out exactly where that turning point is. Okay, so who cares about finding the vertex? Why does it even matter? Well, let's bring it back to that baseball. If this big equation here describes the ball's flight through the air, then asking how long does it take to reach its maximum height, that's just a fancy story way of asking, hey, what's the x-coordinate of the vertex? See? It's the same question. So we bust out our special tool, t equals -b over 2a. We just have to plug in the numbers from our baseball equation. So b is 64 and a is -16. We run the calculation and we get a nice clean answer. 2. That's it. It takes exactly 2 seconds for that ball to reach the very peak of its flight. But wait, how high does it go? What happens at that 2-second mark? Well, we take that number, 2, we plug it back into the original flight equation, and that's when we find it. The maximum height, the peak, the climax. The ball is a staggering 144 feet up in the air. Wow. Okay, so if the vertex is the climax of the story, then what we call the zeros are kind of like the resolution, the ending. This is where the journey wraps up, where our parabola swoops back down and crosses that horizontal line. Or, in the story of our baseball, it's the moment it finally smacks into the ground. Yeah, we call these final landing spots zeros, or sometimes you'll hear them called roots. They're simply the exact points on the x-axis where the parabola's height, its value, is 0. It's the official end of the line for its journey on the graph. So, how do we find these ending points? Well, we've got a couple of tools in our toolbox. For the nice, neat equations, we can often use a simple technique called factoring. But for the messier ones, the really stubborn equations that just don't want to cooperate, we have a super powerful universal tool, the quadratic formula. Let's check in with our baseball one last time. The question is, when does it finally hit the ground? Well, that means we're looking for the 0. We use factoring on the equation, and it actually gives us two answers, 5 and -1. Now, since we can't really go back in time, that -1 doesn't make sense for our story. So the story ends at 5 seconds. That's when it hits the turf. But what if I told you there's a way to get a sneak peek at the ending before you even do all the work? Like a secret code hidden right inside the equation that tells you what kind of ending you're going to get. Well, there is, and it's called the discriminant. This tiny little piece of the big quadratic formula, b squared minus 4ac, it's just unbelievably powerful. It won't give you the exact answer, but it does something maybe even cooler. It tells you the nature of the ending. It predicts whether our parabola is going to cross the x-axis twice, or maybe just tap it once and go back up, or maybe it misses the ground completely. Let's just see how it works. It's really simple. If the discriminant turns out to be a positive number, like, say, 80 in this example, that's your clue that you're going to get two different real endings, two landing spots. Now, if it's negative, that means the story doesn't have a real ending on our graph. The parabola never actually touches the x-axis. And what if it's exactly 0? Well, that's special. The parabola comes down, kisses the axis at one single point, and then heads right back up. A perfect, graceful landing. Honestly, the best way to think about it is this. The discriminant is basically the movie trailer for your parabola story. It gives you a really good preview of the ending, but it doesn't spoil all the details. It just lets you know if the journey is going to have one conclusion, two conclusions, or maybe no real-world conclusion at all. So, there you have it. That's the story of a parabola in a nutshell. It all starts with its equation, which is basically the map for its journey. It hits that big, dramatic moment at the vertex. It finds its end, its resolution, at the zeros. And the whole time, there's this little secret code, the discriminant, that gives you a hint about how the whole thing is going to wrap up. We've followed this whole story, right? From the parabola's simple beginnings all the way to its dramatic conclusion. So now, I want to leave you with a question. As you go about your day, look at the world around you. What other stories, what other real-world journeys do you think you could describe with this one single powerful shape?